Hello, everyone. Good afternoon. Welcome back. Okay, so we're gonna continue our journey into convolutional neural network. We haven't reached the part for the network yet, right? We have done with convolution operator based on this two-dimensional inputs. And we have defined what is strided convolution, right? What the padding is, how the padding plus the stride will determine the size of the output given the input size and the filter size, right? So you can use a simple formula like the output size is the input size plus 2 times the padding minus the filter size divided by the stride rounded to floor plus 1 as the outputs formula. Okay, so next we're gonna look at this inputs that has more than one channel, more than 2 dimensions. Okay, so it's now, what if we have a cube or we have a 3D volume as inputs? Okay, so this is a particular case for input images that are in color. Okay, if it's not a color image, if it's just grayscale, then a 2D matrix is sufficient. But now if we have colors to describe, then we basically use 3 channels, and we call this RGB or RBG channels. R for red, B for blue, and G for green. And the dimension of the inputs is usually height by width by number of channels. Okay, it's usually handled in this. So all the meanings of these 3 dimensions are in such an order: height by width, or sometimes it's width by height. It's depends on the inputs, but usually the channel would be the 3rd dimension. So actually, in fact, this will be the most commonly seen cases for our convolutional neural network applications, because nowadays the image data, the video data are 99% in colored formats. Okay, so with this 3D volume as inputs, accordingly, we need to have a 3D filter. Okay, so in this case, the input is 6 by 3, and the filter is 3 by 3, also by 3. Okay, so note that the last dimension of the inputs and the filter, they must match. Okay, otherwise it will be an invalid convolution operation. Okay, so in order to have a filter applied to the inputs, then we make sure that the filters need to have the same number of channels as the inputs. Okay, so you're wondering why we say matched channels. Why not we just say they must be having 3 channels? Because sometimes the input can have more than 3 channels. So you will see that the outputs of this convolution operation can be a volume that is even deeper or even thicker, that has more than 3 channels. And that very thick volume can also be the input for another convolutional filter. Okay, so in another convolutional filter, then the inputs will be more than 3 channels. Okay, so let's look at this simplest case. When we apply such a 3 by 3 by 3 filter to this 6 by 6 by 3 inputs. The output is just a 4x4 matrix. Okay, note that it's just 4x4. There's no by 3 anymore. Okay, so the principle, the underlying computation is very straightforward. So previously, when we have just one channel as inputs, we will just use that filter as a moving window, right? As a window to slide over all possible positions on top of this input image, right? And we'll do the same thing here. So this time we are not sliding a two-dimensional window, but now it's a three-dimensional cube window, right? We'll slide this cube within this multiple inputs, multiple channel inputs. Okay. All right, that's the first position of the of where we put the filter at. Okay, and then there will be like 3 times 3 times 3, which is 27 elements within that region, like highlighted by this yellow cube within the inputs. So what we're gonna do is to compute the summation of the element-wise multiplication, right, which is similar to the dot product. But now it's just in 3D dimension. We collect all the elements in that 3D space and compute the element-wise product and sum up all the products. All right. And then we move the cube to the next position, do the same computation, and next, just like the way we did for a two-dimensional case. All right. So the result would be a 4x4, because if you use the formula, the inputs is n, right? And the filter size is f is 3. So, and there's no padding, so it should be n minus f plus 1, which would be 4, right? Assuming there's no stride. Stride equals 1, right? It's just the same formula used before. Okay, so now it comes a more interesting application. So actually, we can apply multiple filters to one input. If we apply the convolution filter once, then we will have one 4x4 matrix in this example. What about we simply apply another filter, okay, which is in this little bit dark yellow filter, in this dark yellow color. This is a second filter. And this second filter will also generate some output in the shape of 4x4. Okay, so now we can stack the outputs from both filters. Okay, and we will have a cube or a volume as outputs. Okay, and this new combined outputs here would be 4 times 4 times 2. There's an additional dimension here. This by 2 means that we stack these two matrices together. Okay, and also this 2 corresponds to the number of filters we used. If there's just one filter, we will have a 4x4 by 1, right? So we will not write that 1 here. But if it's 2 filters used, it will generate 4 times 4 times 2. And accordingly, you have 5 filters, for example, used, it will be 4 times 4 times 5. Okay, so this output channel, the number of channels in the outputs is determined by how many filters you have applied. All right, so that's the general principle of applying multiple filters. So again, here let's pay attention to 2 places. Okay, so first of all, the input has multiple channels, and let's use this n with subscript c, okay, to indicate the number of channels in the input. Okay, so there's one match place here, which is that the number of channels in the filter needs to be matched with the number of channels in the inputs. So that's the first match, right? Otherwise, the computation will be not valid. Okay, and the second number of channels is here, is the number of filters actually. Okay, so this n subscript f indicates the number of channels, and this number of channels determines the number of a number of filters determine the number of channels in the output, right? This NF indicates how many such filters, how many of such filters are actually applied. Okay, so this is two different quantities, which is NC and NF. Okay, which together determines how a complete convolutional operation is conducted when the input is a 3D volume. All right, so we have laid out all the fundamentals for defining a convolutional neural network. So next, let's put these little pieces of basic operations together and try to define some more modularized, like small modules of building up the convolutional network. Let's call them convolutional layer and the pooling layer. And using these two layers defined, we're gonna build our first simple ConvNet example. Okay, nice. So let's look at what typically a one layer in the ConvNet should be. Okay, it's typically a set of convolutional filters applied to an input. Okay, so now we have two filters used. So there's one slice of outputs for each filter, right? So there's a 4x4 for the above filter and another 4x4 for the later filter, for the below filter. So given this output, 4x4 output, we're gonna first add a bias B. So this bias is just like the bias term in a regular neural network. This B is a parameter that can be learned. Okay, it is parameter B, and then this big chunk of computation results within these parentheses is something similar to the Z of a regular neural network. And then we're going to apply some nonlinear activation. In this case, for example, we apply ReLU to all the elements of this computation. Okay, then it will give us some activations, right? So you can think of it. This part is the activations, right? These are the Z, these are the activations. And all the activations, if we stack them up, we will have a 4x4x2. And then we can call this the combined outputs here as the activation for one convolutional layer. Okay. And this part is called the so-called Z1. And all right, so where is the W parts? I guess many of you may be concerned here. So the W's are the parameters. Okay, the W are the parameters, are the convolutional parameters. They are just the numbers inside those 3x3x3 filters. Okay, all these numbers are parameters. Okay, so you can think of it as those capital W1 in the case for to the regular, just like the regular network. I see a question. So the B added element-wise. Yes, that's correct. So B is like added to each element within this results of this convolutional operation. It's like broadcast the B to each element in the outputs cells. All right, so it's an analogy to a regular network. Okay, and so you can think of it. Okay, this is our inputs A0, and how we get A1 using this formula, and this formula actually indicates such a complete computation process. implemented by these convolutional operations. All right, so that's one layer of ConvNet, and we can call it a convolutional layer. So when we previously introduced the regular network, let's do some little review here. Okay, so the W1 here, it's a two-dimensional matrix, right? It's a certain number of columns by a certain number of rows. Okay, so the number of rows of W is the number of elements in A1, right? And the number of columns is the number of elements in A0. So it should be a N1 by N superscript 0 matrix for a regular network, right? So it'll be different, of course, in convolutional network. So let's simply look at how many parameters are actually used in a convolutional layer here. Okay, so let's assume that there are 10 filters used, and each filter is 3 by 3 by 3. Okay, so in this case, in terms of the total number of parameters, okay, we should do such a calculation. First of all, everything in that filter are parameters. Okay, so there are 27 parameters in one filter, in one convolutional filter, and then we need to plus this one because this is the B that we add to each filter, right? And because we have 10 filters, so there should be a times 10 outside the parenthesis. So if you put this together, there will be 280 parameters. Okay. So the thing is that no matter how big the input is, the input is a 6 by 6, okay, by 3 small image, the number of parameters used will be 280. But when the input is 100 by 100, then it's still the same number of parameters, okay? Because we don't change, assuming that we don't change the shape of the filter and we don't add filters, that number of parameters will be the same, okay? So this is a huge advantage over regular neural network, okay? Right, remember in the very first slide of this convolutional neural network lecture, we say that if we're gonna use regular neural network, then the size of the number of the parameters is totally proportional to the number of inputs, right? If just a 60 by 64, then it's already 20K of parameters using regular neural network, okay? So that's a huge advantage over regular neural network, okay? So that's a bit of computation for a number of parameters. So that's hopefully that gives you some ideas of how, what's the difference here between a ConvNet and a regular neural network. Okay, so let's look at the further more formally defined annotations, okay, just like what we did with the regular neural network. So we still have the concept of L, okay? Because we have multiple layers. So the L is for the layer, and the F superscript L, of course, it's the filter size, the filter size used for layer L, okay? And the padding for that layer is PL, okay? So this PL can be different options as we discussed before, right? So when no padding is used, it's called a valid con. When the padding is used so that the output has the same height and width with the inputs, then it's the so-called same convolutional, okay? ConvNet be much more common than a regular neural network, seeing as how big some images would work. Yeah, so for for handling image data, computer vision tasks, ConvNet is way more commonly used nowadays. Okay, and stride is denoted by the S superscript L. Okay. So now it comes to the input shape. Okay. So because the inputs can be not like strictly like a square image, right? It could be the length, the width and the height can be different. So we use the N superscript capital H for the height, capital W for the width. Okay. So the inputs we use L-1 because it's from the previous layer, right? You can think of its activations from the previous layer. So we will use this L-1 to indicate the shape of it. So this NC here is critical. It's the number of channels. The C is for channel. Okay. So the NCs is the number of channels from the previous inputs. So it's gonna decide the shape of the filters in this layer, right? Otherwise, there will not be valid convolution. Okay. And also, we need to indicate the output shape as well. It's also an H and W and an NC, but they have different superscripts. Okay, it has superscripts as L. So now let's look at the rules. This part didn't change actually. Okay, so it's just the application of the general principles from the convolutional operator. Okay, so the one thing to notice is that these two number of channels, they are not equal. Okay, so these are not the same thing. Okay, so this is what a beginner is gonna make mistakes about. Okay, so the NC for the current layer, which is the output shape, which is the number of channels in the output, this NC is actually determined by the number of filters used. Okay, if it's 10 filters used, then this NC would be 10. Okay, if it's 20 filters, and it's 20. So it is not the number of channels in each filter. Okay, so about each filter, what's the shape for each filter? It's purely this NCL-1 is purely the input, the number of channels in the inputs. Okay, so the shape of the filter is determined by these channels in the inputs. Okay, all right. And if we want to define some activation, CAL, then it's in the same shape as the outputs of this convolutional operation. Okay, and we can of course vectorize everything, right? When we have, say, M images as input at the same time, then the activation would be a M by that many dimensions as a capital L, which we can call it a tensor, okay, a high dimensional volume in this case. Okay. So in practice, these M are usually like the size of our mini batch. Okay, we can feed the model like 128 images at the same time. So in that case, the first dimension corresponds to the mini batch. Okay. And another two technicality is about the weight. And in this case, the weight parameter WL, we usually refer to these weights as all the parameters in total in the filter. So here, these three is the shape for one filter, right? And because we have that many filters used, so the total number of weights would be like this. And if we want to consider bias, it will be like 1 by 1 by 1 by NCL. So it's like this 1 by 1 by 1 is actually giving its additional some additional dimensions, so that this bias can be applied to each position of the convolutional outputs. Yeah, so it's not the case that height and width should always equal. So it's in the shape of the filter. Yeah. So the most commonly used filter is the filters have same height and the width, but it's okay that a filter have different size, like 2 by 3, 3 by 2. But I don't think that's very often. Yeah. When you implement this in PyTorch other frameworks, it's very flexible to set the size for the filter as well. Okay. All right. So I think we have talked about enough for the building blocks. So without talking about the pooling layers, let's first use the convolutional layers alone to implement some network. Okay. So this example is like inspired by the very first early example called the net. Okay. Which was proposed in basically 1998 by Jan LeCun. So in this case, we will make some changes by not using the pooling layers. Okay, so the outputs. So this just for a simple demonstration of how convolutional layers can be used for image collection tasks, image classification tasks. All right, so let's say we have a color image that is in 39 by 39 by 3 shape. Okay, in that shape, and the number of channels should be 3. So in this case, for the first convolutional layer, our f should be 3. So let's assume we use a f of 3, and we don't use padding, and we use a strata of 1, and assume we have 10 filters applied. So applying the principles from the previous slide, we will have a 37 by 37 by 10. Okay, so this 37 is computed by like 39 minus 3 plus 1 divided by 1 plus 1, right? And the 10 actually comes from the 10 filters used here. Okay, that's a straightforward computation. So the number of channels for this first layer would be 10, and we apply some ReLU out of it, and this A1 would be used as the inputs for the next layer. And the next layer, we have a larger filter. So this time the filter will be 5, still no padding, and we also use larger stride. Okay, and we apply 20 filters this time. So the results would be 17 by 17 by 20. Okay, you see the match relationships now. The 20 matches the 20. Okay, and again we apply some ReLU. That's our A2, and now we're gonna not stop here. We will further apply some very large filters. Filter equals size equals 5, and big stride equals 2, and more filters that will give us 7 by 7 by 40. So all these quantities can be directly computed by the principles we defined so far. Anyway, so far we have the intermediate representations visualized as those cubes, and you can see a general trend is that the cubes becomes thinner and longer, right? Thinner and thicker, right? Not thinner, thicker, but smaller. Like the width and height shrinked, but the depths increased. Okay, then we applied another ReLU, which we get A3. So at this step, we think that the intermediate activations, they are small enough. I mean, in shape, it's very few elements now. It's just 7 by 7 by 40 elements. So we will directly flatten all the elements into 1900, like 1960. So this is the quantity of 7 times 7 times 40. Okay, so we can think of it, these 1960 units as some input to some regular neural network. Okay, we can think of it, this vector contains the condensed information from the output, from the inputs. Okay, so we can think this vector is a representation of the input image. Okay, it contains information about which number that this input image indicates. All right, so it's a very abstract, condensed summarization of the input image. So what we basically can do is to use this vector to make classifications. Okay, so in practice, we're gonna feed this 1960 units vector into some, for example, a neuron or a logistic regression model to make predictions. Okay, so I think this is the very first simple convolutional neural network model that we built. Well, on paper, theoretically, on paper, to make everything make sense, to make the convolutional operation make sense for image classification. Okay, and then the general trend, as I said, the height and the width goes down for each intermediate representation, and the number of channels go up. Okay, so there are two reasons that the number of channels go up. Right, and you see that the two reasons is that, first of all, we're gonna use more filters for later stages, right? And another reason is that the reason for the heights and the width goes down is that we're gonna use the stride to shrink the size. The final vector to the output would be the best executed with the sigmoid function. Yeah, so if it's just for classification, then it's a sigmoid. This neuron would have a sigmoid activation. Yeah, that's a good point. So if we're gonna directly use the output from this neuron, then we're gonna use sigmoid for binary classification, 0 versus 1. Yeah. All right. Okay, so that's a complete example using convolutional layer alone. Okay, and next we're gonna see that convolutional layer is not gonna be it's gonna be just one part for the model, and the next important two parts would be the pooling layer. Okay, and the practice have shown that adding pooling layers into the convolutional network would highly increase the computational efficiency and the actual performance of the network. Okay, all right, so it's called pooling, and there are several different types of pooling, and the most commonly used pooling is so-called max pooling. Okay, and it's very straightforward defined. So think of that the input is this 4x4 matrix, and say we're gonna apply a filter that is 2x2, and we're gonna slide the filter with a stride of 2, which means we go 2 steps, right? Go 2 pixels in 1 step. So what we're gonna output in the max pooling would be a 2x2 matrix. Okay, so what would be the elements in this 2x2 matrix? Okay, the first one would be 10, second one would be 4, the third one would be 7, the last one would be 3. So you see the corresponding relationships now. The 10 in the red cell is the maximum elements within this red region, and so is the 4 in the yellow region. The 7 is in the blue region. Okay, so the max pooling will pick the largest elements in the input region and use that value as the output. Okay, so in another word, it's selecting the most salient value or the most salient feature of the region covered. Okay, so it's a very effective way of picking out the most informative or most salient features in an input representation. So the intuition behind it is that we want to preserve the features, preserve the most salient features while discarding the not that relevant, not that salient values. Okay, so this is a special layer. This is a special layer that has no parameters. So this filter is not like the convolutional filter. This filter doesn't apply some additional parameters, right? There's no W's, no B's, okay, no ReLUs. It's just like select the biggest one element. Okay, so this is a max pooling, right? And we can apply max pooling on the 3D volume as well. Okay, so if we apply a 3x3 max pooling with stride equals 2, stride equals 1 now for this 3x3 volume, the max pooling would output a 4x4x3. Okay, so this is a little bit different than the convolutional filter, right? It's a max pooling, so the outputs would match the inputs. Okay, so this cell basically, the max pooling applies to each channel independently. So this cell in the red corner here is just the maximum elements among this 3x3 region in the red channel. And these elements in this, you can see it, let me use a different color. This cell in the green cell, in the green channel, is the biggest one among the 3x3 channel in the green channel. Okay, and so is the blue one. So it's applied to each channel independently. Okay, so that's the information, so that the most salient information in each color channel will be preserved. Okay, and that's it. That's a pretty straightforwardly defined operation called max pooling. And next, just a variance of the max pooling, we have average pooling. Okay, so I don't think nowadays we use average pooling that's often, because it's kind of blur the input images. It's like we apply the pooling to the inputs, and the outputs for each cell would be the average value for the region being covered. Okay, instead of selecting the most salient one, we compute the average values. So it's not as commonly used than average pooling. All right. So the commonly used parameters for pooling is that we will use stride 2. Okay, which means so when you use a filter of stride 2, a filter 2x2 filter with stride 2, which means you will slide the window, slide the filter on top of the input without overlap, right? We just select the regions, pull the regions independently. But it can also be like filter equals 3, stride equal 2. In that case, there's some slight overlap, but that is sometimes also used. Okay, so but the common thing is that the stride is usually 2. Okay, the stride equals 1 is not that often used, except for some special cases like the inception network we're gonna cover in the future lecture. Okay, so padding is also rarely used. Okay, we don't need to basically padding before applying the pooling. And the most important thing is that it's unlike the convolutional layer. There's no parameters learned. Okay, so before we enter the next section that we introduce some actual networks, we're gonna go through these variants of the net 5 using the convolutional layer and the pooling layer as an example. Okay, for the net example, the original work that Yang LeCun proposed is based on the handwritten digit which is a well-known data set nowadays, and it's a very small input data, like 32 by 32 by 1. And what the net does is to apply a pretty big filter, which is a 5 by 5 filter with stride equals 1. And by the computation rules, it will generate some inputs in 28 by 28 by 6. And this by 6 means we apply 6 such filters. So that will be the first Conv1 layer. So we have Conv1, and correspondingly we have a pull1. So this first pulling layer is like a 2 by 2 filter with stride 2. So that will basically reduce the height and width to half. Okay, and it preserves the number of channels. Okay, because the pulling doesn't change the number of channels, so the 6 is still by 6. So that's the outputs after the first pull. And sometimes we can call this layer the conv plus the pull together as one layer. Yeah, because such a convolution followed by a pulling is a very typical paradigm in convolutional neural networks. Okay, so that's our first layer. And then we apply the same convolutional filter to further reduce it into a 10 by 10 by 16. Okay, that's our conv2, another max pull, which makes even smaller, which is 5 by 5 by 16, and that's our layer 2. And upon this time, we have a pretty small representation, because 5 times 5 times 16 is just it's just 400 units, right? That's 400 units can be treated as the inputs to a fully connected regular neural network. Okay, so we will have this fully connected layer, which we call FC3, which like reduce the dimensions for this 40 to 100 or 120. So you can think of it, this is our input to a regular neural network, and this is the hidden representation for that network. Okay, so that's 120, and we further reduce it to a 84 units using another layer of neural network. And this another layer, the output of this layer of these 84 units will be connected to a Softmax layer that only has 10 outputs. Okay, so again, now we're gonna reach the point that we are gonna introduce this Softmax layer. Okay, so this Softmax is used for making multi-class classifications. Okay, in the next slide, we're gonna have a review of it. Okay, so that's the output for this network. Okay, so this network is basically the original work applied, proposed by Jan LeCun in 1998, and it's still a very classical model for simple image classification tasks, and it's also a paradigm, provides a paradigm that's most of the modern convolutional networks follows. Okay, all right, let's take a look at this number of parameters in this LeNet. Okay, use the formula we defined for ConvNet. It's easy to compute number of first ConvNet is that number, and the second it'll be that number, and you can see that the majority of the parameters is actually in these fully connected layers. Okay, because the fully connected layers are those W's. The W's is just n L minus 1, L NL by NL minus 1. So when the L minus 1 is very large, for example, in this case, the outputs of the pooling will be 400. Okay, so this FC would be 120 times 400 plus the bias. So this will be a lot of parameters here. Okay, and the convolutional part, the convolution part, actually have only a small set of parameters. Okay, and that's it for the number of parameters. So I think from the next slide on, oh yeah, so this is another, I'm wondering why there's a replicates. Okay, maybe I forgot to delete this one. Okay, so another piece of information here is that the original work is that it use average pooling. Okay, so an improved version is to use max pooling. Okay, as shown in the previous slide, and in the original paper, sigmoid and a 10H are used for activation, but now we would typically use ReLU. Okay. And also they don't have nonlinear activation. So these are just the variants of the original model. All right. Okay, so I think that's so much for the basic parts of convolutional neural network. If there are any questions at this point, you can let me know in the chat. Yeah. So to studying what those images look like what are the patterns, what are the encoded information in the outputs of a convolutional layer, I think it's there is a group of people or a group of research field that are interested in that topic. So it's like basically to interpret the results of convolutional layer, or to explain why convolutional operations works for image classification. So this is quite a big research field, and usually speaking, a common conclusion is that when we have multiple layers, I think I have mentioned that when we first introduced regular neural network or deep neural network. It's like when we have a deep model that have convolutional layers in each layer, then the later layers usually capture information that are more abstract. Okay. Like given a human face as inputs, maybe the later layers can capture higher level features, like whether this is a female or a male face, like those high level features. While the earlier layers, the earlier convolutional layers, they capture like shallower features, like whether they're like the color, like the lightness, like the edges detected, and the intermediate layers, they try to, so it's like the level of abstract goes up, okay? But I think why ConvNet work is still a active research field that people actually don't really have very clear interpretations, very clear explanations of why ConvNet works well on image representation. Okay. So yeah, but that's a good point that you raised. The same question also occurred to not just convolutional neural network, but also to a recurrent neural network or attention-based models that model human language. It's like people are curious about why those large neural network-based models can model the meanings of words, can model the meaning of sentences even. So it's an interesting area. Okay, and there can be a lot of work to be done. Okay, so let's look at these more advanced ConvNet network examples. Okay, so hopefully we can cover the AlexNet, VGG, and the ResNet today. So I will probably leave the one-by-one convolution and the inception network into the next lecture. And also in the next lecture, we're gonna have an introduction to the actual applications of ConvNet using object detection and other tasks as an example. Okay. So before that, let's have a review for the Softmax layer that we mentioned. Okay. So this softmax regression is a kind of technique that we talk a little bit about when we introduced logistic regression. So logistic regression is for 0 versus 1 classification, but softmax is for multiple classes. So in modern image classification tasks, in data sets like CIFAR 10 or CIFAR 1000, CIFAR 1000, they have a lot of labels. So in this CIFAR 10, it's 10 categories of animals or objects to be predicted. Okay, so the output labels, we can use integer numbers from 0 to 9 to indicate different labels. Okay, so this softmax layer, we use this example to show that the size of outputs of the softmax equals the number of classes. So in this case, we will use a smaller number 4, okay, just for showcase. Say we want to predict whether an image is airplane or a bird or a cat or a dog, okay? Say we have a complete network that we can take the inputs X to the network, and it's gonna output like 4 units in the output layer, okay? So these 4 units should represent the probability that this data X should be a airplane versus a bird versus a cat versus a dog. So this Y hat is a 4-unit vector. Okay. So how we come up with these values for the 4 units of the output layer? Okay. So it actually can be decomposed. The last layer can have will first have a linear part, okay, which we write as ZL. So this is typically what we wrote for a neural network, right? So the ZL is the activations from the previous layer times WL plus B. Well, that's no different from a neural network, right? So the Z is already a 4x1 vector. So now the activation part will be different. It's not a sigmoid. It's not a typical sigmoid function because it's not a binary classification. The activation parts, we will do such a conversion, okay? We will compute T as e raised to the power of ZL, okay? So you can think of the left part is ZL, okay? So the Z is a 4x1 vector and the T will be e raised to the power of ZL, okay? So the T alone is also a vector. Okay, T is also a 4x1 vector. So we will have T1 to T4, okay, for each unit. And then we're gonna compute the actual activation AL in such a way, okay? So AL would be the T divided by this summation of all T's, okay? So the denominator is for the purpose of normalizing, okay? So the AL would be a 4x1 vector. And AL has such a property that all the elements in AL add up to 1, so that it represents a valid probability distribution, right? The probability is normalized to 1, so that they are valid values. All right, so that's AL. Like if we use a concrete number as example, say if we have ZL at the beginning in such a values, and we can compute T by raise e to the power of ZL, that will give us such a value for T's, okay? So we can see very extreme values because e to the power of 4 would be a very huge values, okay? But this is not probability yet because they don't sum up to 1. They are not within the region, within the range of 0 and 1. Okay, now we're gonna compute the summation of all T's and use that to normalize T so that we can have AL in a normalized manner. So all elements are ranged within the range of 0 and 1, and they all add up to 1. So this AL is now a valid formation for the probabilities. So these probabilities means that the input data belongs to an airplane with the probability of 84%. So it's very likely that the input data is an image from airplane. All right, so that is basically how softmax activation are defined. Okay, so let's look at a little bit about the loss function. Okay, it's different from the sigmoid function because it's not a binary classification, but it's somewhat related. I think this is also revealed for the softmax for the logistic regression parts. When we introduce logistic regression, we introduce the multinomial regression, which is just another name for the softmax regression. Okay, right. So assume that we have in the first case, we have a prediction like this. We have 0.84 as the probability for the first category, say airplane, right? And the y without the hat, the y is the ground truth. Okay, so the y is a one-hot encoding, which has a 1 and 3 zeros. Okay, so the y indicate that this is actually a plane. So with this prediction, we're actually happy because it assigns the highest probability to the correct position, right? To the correct prediction. Otherwise, if the ground truth is the second category, which is maybe a cat, maybe, right? So we're unhappy about this. So we're going to compute the loss function so that the loss will give penalty to the bad predictions and encourage the good connections, good predictions. All right, so how we're going to do this is to use the term cross entropy loss. Okay, so this cross entropy is the summation of y times logarithm of y hat, and give a negative negative operation to it. Okay, so it's basically a measurement between the output distribution and the actual distribution. The output, our prediction is y hat, and the actual distribution is y. So the larger the deviation is, the larger the difference between y hat and y, then we will have larger cross entropy loss. Okay. So in the case 1, the loss would be negative log 0.84, right? That's a fairly small value. Okay. But in case 2, you will see that if you compute the loss, the likelihood, the log function of this 0.004 with a negative symbol, it will be 3 point something. So this compared to this one, the loss is pretty large now. Okay, so that's how the cross entropy makes sense. Okay, and if we visualize it furthermore, we have Z's and A's, right? For the last layer, the loss will be like this, and we're gonna like backpropagate the gradients of the loss with respect to the intermediate variables, right? We want to know the loss, the gradients of the A's. So it's basically, if we take the derivative with respect to the log function, it'll be gone. It will be like negative yi divided by ai, right? And we can use the chain rules to further backprop the gradients to the layer z's. Okay, so it will be a bunch of gradients of a times the partial derivatives of a with respect to z. Okay, so this is something we're gonna compute. So I'm not going to the details, but decided by the formula of softmax, we can derive these gradients with respect to z like this, and it will be eventually in a pretty simple form. Okay, it will be ai minus yi. So this may remind you of the logistic regression, right? In the logistic regression, when we use computational graph to compute the gradients of the z, which is dz, is actually the same form as this softmax regression. So the softmax regression is actually very close related to the logistic regression case. All right, that's some review for the softmax function. Okay. Now we have time. Let's take a look at all those more advanced network. Okay. So first of all, in the year of 2012, AlexNet is invented, and it's basically a revolutionary achievement that uses the deep convolutional neural network to improve the accuracy of ImageNet classification by a very significant amount of accuracy in improvement. Say we have 200 by 27 by 227 by 3 input images. So that's the image as image size in the ImageNet datasets. And then AlexNet actually uses very large filter. It's a 11 by 11 filter with large strike as well. So that will be the first intermediate variable. And max pool is applied, which results in smaller intermediate representation. And we will apply a same ConvNet to make it deeper, right? And again, a max pool, okay, into a smaller 13 by 13 by 256. And again, the same ConvNet into a much deeper, even deeper, okay? And again, a save ConvNet, okay? So a lot of save ConvNets used, and then the max pool, okay? And which results in a 6 by 6. So that's the point that network gonna flat all these images, flat all these elements in this long vector that has 9,000 images, 9,000 elements into this fully connected network that has 4,000 units, okay? And these 4,000 units will be connected to another fully connected layer, which feed into a softmax layer that has 100 outputs, okay? So because at that time, the ImageNet has, in the ImageNet dataset they use has 100 labels to be predicted, okay? And the number of parameters, if we compute it, it's actually pretty huge. It's like 6 million parameters used, okay? And that's a lot of parameters, okay? So given these 6 million parameters, first of all, it's not gonna be easy to tune the network, to train the network, okay? So as we mentioned before, when the network goes deep, the gradients, when it passed from backward to like from the later layer to the previous layers, the gradients, it's easy to get exploded or vanished, right? So it's tricky to train such a network. And also such many number of parameters also indicates the possibility of overfitting to the data, right? But somehow they overcome all the difficulties by increasing the accuracy, like by 10%, which is a significant improvements at that time, okay? Which means that the computer vision tasks is becoming a very mature and reliable techniques. Okay, so that's AlexNet. So like as I mentioned before in the previous slide, how do we like overcome the overfitting issue? Okay, so what the authors have applied is that they used a lot of data augmentation, like created duplicate, like create different versions of the same image by mirroring it random cross. Okay, and basically they increase the data sets by a factor of 2,000, which is a lot of work. Okay, a lot of data generated, and also they use dropouts. Okay, remember dropouts in the when we talk about the when we train in the previous chapter for tuning the deep neural network, right? We can like randomly drop out some units. Okay, so dropout is applied to all the regular neural network layers. Okay, so dropout is not applied to the convolutional layer. Okay, convolutional layer won't be dropped out because the parameters are already very small parameters, very few parameters. So the dropout is basically applied to the fully connected layers. Okay, in order to deal with the overfitting issue. Okay, so that's for AlexNet. So I think I'm gonna finish the VGG nets, and we'll leave the residual net, the ResNet, to the next class. Okay, so VGG nets is followers after the AlexNet came out in 2012. So it's in 2014. So it's a very deep, even deeper than AlexNet's convolution layers for large-scale image recognition. Okay, so in VGG16, in this network, they basically used more uniform layers. Like for all the convolutional layers, they used fixed filter size as 3 and 2 padding and the stride, so which basically is the same convolution. And for the pooling layers, they fixed the pooling layer to max pooling, and they use the filter size equal to and the side stride equals 2. Okay, so that's how they did it for the first couple of layers. Like it's a very uniform setup. Like they used ConvNet 64 conv filters after followed by a pooling, and 124 conv network conv filter, convolutional filter followed by a pool, and they basically repeat this step for multiple times. Okay, until they reach the parts that they have that 25,000 units. They flatten to a fully connect layer, another fully connect layer, and a softmax that has 10,000 labels, 1,000 labels. So that's a huge amount of computation in those fully connected layers. So they use 16 layers that have total number of 138 million parameters. So that's an amazing number of parameters. And they reached a pretty good application, pretty good performance compared with AlexNet. And still nowadays, VGG16 would be a useful network, not just for building models from scratch, but the models they have trained, right? The models they have trained that contains all those useful parameters will be used as pre-trained model that helps to obtain useful encodings or useful representations for images that are used for later classification tasks. But we don't need to basically train the model from scratch. So that's the so-called the paradigm of using the pre-trained model and to fine-tune the model's parameters, like by changing these parameters only for a bit of for only a small part of it, and then in particularly to tune the parameters for our specific tasks, but not for the complete tasks that originally trained the model. Okay, so that's the VGG16. And in the next lecture, we're gonna talk about this ResNet, which I think is a more significant contribution to the area of convolutional, of computer vision, and also machine learning in general. Okay. All right, that's a lot of content today. We have make a big step from basic convolutional operations to like complex models in VGG, like VGG or AlexNet. So nowadays, these models are available online, and most importantly, they're available. The pre-trained models are available so that you can directly download and use for your own task without needing to train the models yourself. Okay, so that's a lot of convenience provided. All right, I think I'm gonna stop recording now. If you have any questions, you can raise it here.